All right. So, everybody ready? Set. Go. Can CH4 act as a nucleophile in an SN2 step? Then we're going to think of why or why not. Okay. No is the correct answer. Why would that be? Yeah, so it needs some electron density around it. And more important than just the electron density, it needs to have that density in a form that can move around and make bonds, right? Or more specifically, it needs it in an orbital that can then form bonds, right? And so what's the leading way for that to be possible? It to exist as a lone pair, right? Okay, and CH4, no lone pair, right? What's the other way that that could happen? Needs to be some form of delocalized electrons, okay? So you have to have it in a form of delocalized electrons. Lone pair is by far and away the most common, but you can also have things like pi bonds and stuff, okay? Okay. Does anybody have any questions on that? Was that at all unclear? Okay. Okay, so let's compare the proton transfer step to the SN2 again. I guess this was actually where I was before, wasn't it? So what are you noticing about bases and nucleophiles? Does that look very different? No, it looks really similar, doesn't it? Yeah, it's damn near the same thing, right? Just in one case, we had a proton, real mobile, real lightweight, right? Can move around easier. The other case, we have a much larger group, don't we? In this case, a CH3. Okay? So, nucleophiles are very, very, very analogous to a base, aren't they? Okay? And so they're both electron rich. When you look at it, it's going to be attacking something and giving its electrons to something that's very electron poor, right? And so in this case, we have an electrophile, which is our substrate, being attacked by the nucleophile, don't we? In this case here, we have the acid being attacked by the base. Note that if you actually use the definition for a Lewis acid and base, it's even more similar, isn't it? Yeah. In fact, it's almost the same thing. Oh, is it a wasp? Yeah? Okay. Sorry, guys. That one's a little high for me to get. I'm going to have to bring my, I have a salt shotgun. I'll have to bring that in so I can. Yeah, have you guys ever seen the salt shotguns? Yeah. Yeah. Not, it's a low power one. It's meant for insects. Yeah. When we talk about Lewis acid and base, Lewis base actually is an electron donator, isn't it? Lewis acid, an electron acceptor. What's the difference between a Lewis acid and base and, for example, a nucleophile electrophile? Can anybody tell me the difference? It's really, really small. Basically, it's how well the electrons can come out and reach things. Okay? That's the only real difference. In a Lewis base, the electrons don't have to be super mobile to reach out and make bonds. In a nucleophile, they have to be a bit more mobile to be a good nucleophile. Okay? But that's pretty much the only difference. Yeah. So let's draw the SN2 step that would occur between these two compounds right here. And so the first things you have to figure out are what? You got it. Nucleophile, electrophile, leaving group, right? Those are your pieces that you got to figure out. Once you have those pieces, every other step is much easier, right? Really, it's the same thing over and over after those pieces are figured out. Okay. And so what's your nucleophile? The sulfur, exactly. One of the things that really gives you a hint here is metal, right? Because dang, metal is just going to lose its electrons, isn't it? Okay. Once the metal loses the electrons, I'm going to be left with a sulfur. You guys okay with me putting little lines here for the electrons?
Yeah.
Okay. Can you understand those okay? Okay. Yeah, if I try to make dot, it just pops up options. Yeah. And so this is going to be a negatively charged sulfur with a lone pair, right? Once that metal goes away. So that's actually a very good nucleophile, isn't it? Yeah. Okay, so what's the next part? Where is that going to attack? Yeah, that's going to attack that carbon, right? Okay. And then what's going to happen after that? Got it. Leaving group leaves. Okay, so let's go ahead and put that all together. We have the CH3S. We have a lone pair, right? And that's going to have a negative charge. Everybody okay with that so far? Okay. And then that's going to react with the C6H5 CH2. And I'm going to go ahead and put a bond here so you can see the iodide leaving a little easier, okay? Okay, because that's the important parts we need to work with, isn't it? All right, and so I'm going to take this lone pair here. Good grief. There we go. And I'm going to draw it attacking that carbon, right? Once it attacks that carbon's going to have more than an octet. It's going to have more electrons than it can hold, isn't it? And so one of those bonds has to break. Okay? Which one's the one that's going to be most stable breaking? It's going to be the one to the iodine, isn't it? Because that iodine can hold on to the electrons real nice because it has pretty good electronegativity and it's very large, right? So it's very stable holding on to the electron density. Okay, and that's actually our reaction step right there, isn't it? It's the mechanism. Okay, so we're going to put an arrow now. And this is going to go, so we'll have this C8, this C6H5, CH2. Then what's after that? Is the I still there? No, the I got replaced, right? Or substituted. Okay, that's where our name comes from, isn't it? Substitution. And so what did it get substituted with? Sulfur. Does it have a negative charge or a lone pair anymore? No, that's bonded on there now, isn't it? Yeah. Yes, we have that bond. Okay. And so what else is with that sulfur, by the way?
CH3.
Yeah, the CH3 is on that sulfur, isn't it? And that just stays with it. Okay. Okay. And what else is there? Now drifting off on its own. Yeah, iodide, right? Iodide now is just drifting off on its own with that lone pair, right? That extra lone pair. Okay. Okay. Does anybody have any questions about that? Mm-hmm.
What happens with the sodium? Is that also just drifting off?
Yeah. We can actually, before anything, we actually just took that sodium.
Yeah, it turns into the...
And we just turned it into a spectator.
Right.
Yeah. Because that sodium is going to be here, drifting off around in solution. But we also would have had it over here, wouldn't we?
Mm-hmm.
And so those are spectators. And they can get just ignored. Okay? Or another way of saying it, it's on both sides of the equation. When you have something on both sides of an equation, you can subtract it off and it disappears, right? Yeah. Okay. It's like having plus x on both sides. Not meaningful, is it? Yeah. Or a +1 on both sides. Well, goodbye 1. Okay. And that right there is just it printed, typed, so it looks really nice. Okay. Anybody have any questions? No? Right. Fantastic. Okay, so this is the bond formation or coordination and bond breaking or heterolysis. First off, note the naming of that. So coordination is going to be where we take 2 electrons from one thing and we form a bond using those 2 electrons from one thing. Okay, it's a bit different than normal bond formation, right? Because normally we take 1 electron from each atom, don't we? Okay, so this is what's referred to as a coordinate covalent bond or coordination bond forming from electrons on only 1 atom. Okay, now the bond breaking heterolysis, what does hetero mean? Different. Yeah, homo meaning same, right? Hetero meaning different, okay? And so lysis means to break, doesn't it? Okay. And so this actually tells us that we're going to take the electrons in one of the bonds, and they're going to go to only one of the species, one of the atoms. Okay? On the other hand, the other atom doesn't keep any of those electrons. Right? That's that bond breaking step we had been doing in each of these reaction steps so far. Okay? Where the electrons in the bond only goes to the, in our case before, up here the iodide, right? It broke in only one direction. If we had a homolysis, that would be breaking evenly across it. 1 electron goes to one side, 1 electron goes to the other side. Okay? Okay. By the way, does everybody remember your bond enthalpies you did stuff with in like general chemistry? Hess's law, etc.? Eh? Okay, where you like broke the bond and 1 electron went to each side? Yeah. Those were homolysis. Okay? That was all homolysis stuff. This being the heterolysis. Okay, anyways, right here we're going to have the bond formation. It's the Lewis base coming together with a Lewis acid, nucleophile with an electrophile. And so we're going to donate a pair of electrons into our bond here. And again, that's going to be that coordinate covalent bond or coordination happening. Here we have what's called the Lewis abduct, or another way of saying that, that's that intermediate before the bond breaks, right? Okay. Right here, we have a coordination step. This is going to be where 2 electrons are going to come into a bond, in this case with aluminum. This is a very typical Lewis acid and base. Okay? Reaction. Everybody see that okay? Fantastic. Okay. Note that if we start off with a positive and negative charge, we end up with neutral, don't we? If we start off with neutral, what do we end up with? A positive and negative charge, don't we? Yeah, because one of them's going to always gain an electron, one of them's going to always have a formal charge that goes down, one that has a formal charge that goes up. Okay? All right, so this is the heterolysis step, or heterolytic bond dissociation step, if you want to go a lot of words to get the exact correct meaning. Everybody will actually understand you if you say heterolysis, which is also the correct thing to say. Okay? But heterolytic bond dissociation step is the long way to say that. And again, everybody will know exactly what you mean. Okay. All right, so we're going to take 2 electrons from a bond, and that's going to go to our leaving species. This is going to leave you with a positive charge. Everybody okay with that? Okay. Okay, what if we have something starting off that has formal charges on it? The one that gets the electrons is going to keep that negative charge, right? The one where it lost the electron is going to end up keeping that positive charge. Everybody say it okay? Okay, fantastic. Okay, so let's talk a bit about nucleophilic addition and nucleophile eliminations. This right here is a nucleophilic addition. And so in this case right here, we're adding a nucleophile. Notice the next step actually doesn't have anything leaving. Can everybody see that? Nothing actually comes off here, does it? And so this is not actually a substitution, because we don't substitute one thing for another. We just add on to it, don't we? Okay? And so we have a nucleophile adding on to an electrophile. It's going to break one of the double bonds right here. See this double bond for the carbonyl, the oxygen. And that's going to go up onto that oxygen. Anybody ever heard of an oxyanion hole, by the way? No? Okay, that's okay. So when you hear of oxyanion holes later, you'll know this exists, okay? That'll be in a more advanced course. Okay. So again, we're going to have a nucleophile. It attacks an electrophile. The only difference between this and our SN2 reactions is that when we break the bond and it goes on to what would have been the leaving group, it doesn't leave. Okay? Because it still has a bond attached. All right. Everybody good with that so far? Can you see that? It doesn't leave? Okay. Okay. Nobody's seeing it leaving? Okay. Thank goodness. All right. So let's go ahead and talk about another nucleophilic addition. Right here we actually have water doing the acting as the nucleophile. And again, we're attacking here. We add on. Again, the double bond comes up, has a negative charge on the oxygen, and that leaves us with our product right here. Note, in this case, it does establish an equilibrium because it's not energetically significantly more favorable to go to product. Okay? It's actually energetically unfavorable to go to product. All right. Okay. And so this is another nucleophilic addition. Is everybody good so far? Break the bond, charge goes up. Note, what are you noticing about where the charge ends up on these things? Exactly. It's the more electronegative species. Yeah, that's how you predict that. It's the same as assigning formal charges, right? Remember when you assigned formal charges back, way back in the day? Back when you first learned Lewis structures, right? Yeah, that's what this is. This is the overall nucleophilic addition steps. Note that nucleophilic additions usually put you in an unstable state. It's going to be an unstable intermediate almost all the time. Okay? And so right here, what are you seeing about these things? They don't look very stable, do they? No, they don't look very stable. And so yes, there almost always is another reaction step that's going to happen immediately after these. Okay? And that's why we keep referring to them as nucleophilic addition step. Oftentimes there's going to be an elimination step after this. Okay? All right, so let's talk about the elimination step. So we have this charge on this oxygen. It can come back down and form that double bond, can't it? We know that because we just saw it in a double bond, didn't we? Okay. Now, what's going to happen here is that when it tries to establish this double bond, that carbon's going to have too many bonds to it, isn't it? And the thing that can leave the easiest, that's going to be the most stable to leave, is going to end up being what leaves. Because it'll be the most energy coming back out, won't it? Okay. And in this case, which is the most stable leaving group? Chloride, right? Okay. And so the chlorine is going to be the one that takes the electrons, and it's going to leave. Now, you may be looking at this as an altogether thing and going, Dr. Clausen, why the hell did the electrons bother moving? Why didn't we just go straight to the end product? What moves fastest? Electrons or atoms? Yeah, when you write in your book, what do you move? The stylus? Or do you move the book? The stylus. Why do you move the stylus? Smaller, lighter, right? Takes a lot less energy. Okay, how about the chair versus the desk? You move the chair, right? You don't bother moving the desk usually. How about the room versus you? Go to the next class. Do you move the entire building so you're in the next class? No. That would be the difference between a electron and an atom, just hydrogen, right? Would be a 10, along the lines of a 10,000 difference, right? In mass. So it would be like saying, instead of moving myself, I'm going to move several of the buildings on campus. Does that make any sense? I'm going to lunch, guys. Okay, rearrange the lunch hall. Bring it up to me. It doesn't make any sense, right? And so when you have reactions that the electrons can move first, these delocalized electrons exist, and they can move to minimize energy first, they're going to do that. Okay? And you'll get an intermediate, and that intermediate is going to be those electrons having moved first. Okay? They're then going to come back down once other stuff gets a chance to move. Okay? Is that making sense so far? Yeah. So we always have to break these up into multiple steps where we have these delocalized electrons that can move. Okay? Okay. Let's look at this one now. So right here we have the elimination step, and what we see is a water over here, right? See, that's an H2O. And over here we have an amine. Okay? And so the electrons are up on the amine right now, and they can go down into a double bond, leaving a positive formal charge on nitrogen, and they can get rid of the positive formal charge off of the oxygen. Everybody see that okay? And so they're going to do that because the formal charge wants to be on the less electronegative species, doesn't it? Okay. Is that making sense so far? Okay. Am I losing anybody here? Okay. Kind of, maybe. All right. So let's talk about bimolecular elimination steps. These are going to be E2 steps. Notice these previous ones, these additions, only had one thing coming on or leaving at a time, right? We didn't have to have two things coming together to have these many of these steps occur. Okay, so when we have to have two things coming together at the same time, these are going to be the bimolecular elimination step. Note here we have a strong base coming together with our substrate. Is everybody okay with that so far? Okay, two things coming together, that's where the two comes from. They're going to, again, be an elimination, right? We establish a double bond and eliminate a species from our substrate. Mm-hmm.
And bromine is the most stable atom that's leaving?
Exactly. Yep. Bromine ends up being the leaving group because it's going to be the most stable when it leaves. Yeah. Okay. It is much more stable than our strong base, right? Okay. A good way to look at these are actually acid-base reactions. So every acid-base reaction goes towards the weakest base, weakest acid pair, right? Okay. So in this case right here, we have a strong base. This right here is a very weak acid, right? Okay. And so what's going to happen is our OH is going to attack the proton right there. Okay. Now, this proton is right next to a positively charged carbon. Can everybody see the positively charged carbon? It's the carbon attached to the bromine, right? That always had a partial positive charge. And so what's going to happen is the electron density in the hydrogen to carbon bond is going to get pulled over so it's shared with the partially positively charged carbon next to it, right? Remember those inductive effects I had been talking about? Where it's pulling the electrons in those? This is actually that being happening, right? Okay, and what's going to happen next is when this electron's density is flowing over to that other carbon, it's making that other carbon more negative, isn't it? And this is going to allow the electron density in the bond going between the carbon and bromine to move off onto that bromine, right? Giving us the bromide leaving group. And then that's going to leave with that negative charge. So a logical course of events. Everybody okay with that? Okay, fantastic. And so altogether, this gives us our E2 reaction, in which we're going to have an OH and strong base that takes an acidic proton that will give electron density that goes into a double bond, and then a leaving group will leave. Okay? Okay. Notice that when you do an elimination, you actually have to have two things that are leaving, right? From our end structure, our product. Okay? Because you're going to make a double bond across that. So in this case, we have an H and a Br that leaves. Okay? Everybody okay with that so far? Right. Okay. All right. And where will that double bond be created? Is it going to be created against two carbons that are like 1, 3, 1, 5? No, this has to be across two carbons that are right next to each other, right? These electrons are going to have to be able to get sucked through that bond to that positively charged carbon. Okay? So it's always one of the adjacent carbons that this is going to happen to. Everybody see that all right? It can't be one's way out here, right? Okay. Okay. And remember, the reason those protons are more acidic is that carbon is partially positively charged. It has been pulling the electron density in those hydrogens, right? This entire time. Okay. Okay, so these are more E2 examples. Anybody see anything that throws a wrench in their understanding of this? Everybody see these are nice leaving groups here? Nice leaving group, nice leaving group. Okay. One of the important parts of this is you either have to have an incredibly powerful base or a pretty good leaving group, okay? Like, they have to have one of the two to do this. At the minimum, you have to have a good leaving group with a strong base. Okay? Mm-hmm.
What is it that makes it a strong or good leaving group? Is it like electronegativity? So like wants to just take an electron and leave, or like
Partially. It's electronegativity combined with the ability to distribute that electron density and be more stable that way. So it has to be quite stable with that electron density. For example, this just outright has a lot of electronegativity because it's the positively charged nitrogen, right? If it was regular nitrogen, not really. But this one right here is actually not that electronegative, is it? No. And so, yes, it's electronegative, but it also is big. And so that charge is very diffused across that large bromide. Okay?
so it'd be stable leaving?
Yeah, it'd be stable leaving.
Okay.
So this state right here is very low energy. It's very stable as its conjugate base.
Okay.
It's the exact same thing that makes the acid-base reactions work, okay? So when you look at these, if it has, it always trends towards the weakest acid-base pair, just like any other acid-base reactions. Is that making sense?
A little bit.
Yeah. So for example, this right here is a much stronger base than this one. Okay?
So it's wanting to make the weaker.
Yeah, it always ends up as the weaker base, weaker acid. And that's definitionally true, actually, because what makes a strong acid strong base is that they do the reaction. Right? That they disassociate a lot. Okay? Another way of considering this is, so good leaving groups are good leaving groups, the same reasons that they would be a good acid, right? For example, this is a good leaving group because it's very stable that way, whereas if it had an H plus on it, it wouldn't be as stable. That making sense?
Yeah.
Okay. Okay. And a similar thing for these right here. So again, we have a stronger base going to a weaker base. Okay? Okay. And all of these terminologies are really, almost all the terminologies that I've been giving you guys are overlapping, right? There's very little differences between these different terminologies. In this case, it's just outright the strength of the base that matters, right? And can anybody tell me why it wouldn't matter it being a nucleophile or not for this? What was the difference between a strong base and a strong nucleophile? It's polarizability. It's ability to reach out and form a bond, right? Okay. Is there anything blocking access to these hydrogens here? No. So we don't have to have as good of an ability to reach out and form bonds, do we? Yeah. And that's why it's just the strength of the base that's all that matters. Yeah. Okay, so let's talk a bit about electron-rich to electron-poor sites in our E2 step. Here again we have the base. It's going to be attacking an electron-poor site. Now notice there's two electron-poor sites here. There's the hydrogens that are adjacent, right? And then there's the carbon right here. Those are the electron-poor sites. And so who here thinks there might be competition between those two sites? Okay. Who here thinks there might be some competition between these sites? Yeah, there's competition, right? They're electron-poor sites, electron-rich attackers, aren't they? Okay. What would determine which one gets attacked, by the way? Yeah, how easily it can reach in and do it, right? Like, you guys have all been through school shooter training. Yeah. I hate using this example because it's really kind of awful morally to use, but it's something I can assure that everybody knows really well. Oh, watch out for the wasp. Hit it. Nope. Oh, missed it. Okay. It's something that I can be assured everybody knows. For example, why do you keep all looking at the wasp when it gets near you?
It's danger.
He's cute.
Is it dangerous to you guys when it's over here with me? No. So it's the one you have more access to is determinant of the one you attack, right? Okay. Same thing's happening here. So when you have a base, it's a strong base, it doesn't have necessarily the ability to reach in and attack something that's a little hidden like this carbon, right? On the other hand, a strong nucleophile is going to have orbitals that can reach in there and attack it. Okay? Okay, and so again, this is the overall electron-rich right here, which is our base. This right here is going to be the electron-poor site, which is our carbon. It is moving electron density away from that hydrogen. And then our substrate is again going to end up being the electron-rich when it leaves, right? Our leaving group is going to leave with that electron density. The important part here is it needs to be a worse base. This needs to be a worse acid. Okay? Okay. All right. So we have a worse acid here and worse bases here. Okay? Okay, let's go ahead and look at some electrophilic addition now. So, in this case, we're going to have a electrophile which can attack a pair of mobile electrons and form a new bond. Notice addition is adding stuff, right? Elimination, we eliminated stuff and made double bonds. Addition is going to be taking usually double, triple bonds. And we're going to be adding stuff, therefore getting rid of the bonds, right? Okay, so electrophilic addition. Again, we're going to have a pi bond. This is going to donate our electrons because those are electron-rich, aren't they? And we're going to have different species of electrophiles. These are going to have positive charges typically, and they're going to pull electrons to them. Okay? All right. Anybody notice what the electrophile can be also called? It could be a Lewis acid, right? Remember your Lewis acids from back in Gen Chem? No? That's okay. That's okay. That's why we go over the stuff again. Okay. Now, the immediate product to these electrophilic elimination steps, the electrophilic addition step, is going to be a carbocation, because when we pull the electron density out of that double bond, it's always going to end up leaving one of the carbons with a positive charge on it, right? Everybody said okay? Okay, so again, we have the electrophile. It's going to pull the electron density out of that pi bond, and it's going to form a bond with one of the carbons. The other carbon, on the other hand, is lost an electron, hasn't it? Yeah. And so it's going to end up with a positive charge. That's what we refer to as a carbocation. Okay? All right, so this is some more examples of this. And again, notice again, we can use, like, for example, HCl. This is an acid. We have to have something that doesn't hold on to its electrons particularly well. So a triple bond in this case. And it's actually going to pull electron density out of that triple bond. Everybody say okay? Okay. And we'll actually add a hydrogen on here. Okay, this is another example. In this case, we're actually adding a nitro group onto a ring here. In this case, this is actually benzene we're doing it on. This is actually a very, 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 very energy intensive reaction, because we're breaking the benzene ring, aren't we? Everybody see that okay? Uh-oh, broke the benzene ring. That's very stable, isn't it? Okay. Okay, so let's talk about carbocations a little bit. Now, in electrophilic elimination, we can actually have the carbocation creating the electrophilic elimination. So again, the carbocations are very unstable. They're very high energy. This is not something that a carbon typically is going to want to be, right? Sitting there with a positive charge. And so the reverse of the electrophilic addition is actually a very common elementary step as well. And this would be an electrophilic elimination. Again, it's going to end up taking this carbocation. It's going to pull the electrons from our E species, which will end up being an electrophile, right, when we make it. And this is then going to form a double bond. So notice that we're actually representing the two different directions for this step in this point. Okay? So we have the carbocation forming an electrophilic elimination. We have the electrophilic addition, which forms the carbocation. Okay. Here's some more examples of this with actual species that are doing these things. And so, for example, we have our carbocation in our benzene here. And we have right here something that can act as a leaving group right there. Okay with that? And so we eliminate this new electrophilic species. This leaves us with our nitrobenzene. Over here we have water. Water can act as a reasonably decent base, right? And so we're actually going to end up with one of the protons here being positive and acting as an acid. Okay. This will pull the electron density from that proton carbon bond into a double bond and leave us with H3O+. Okay. Now, that H3O+, that is an electrophile, isn't it? Yeah, we'd used that as electrophile before. But it's all dependent on which species is going to be more stable. Okay? All right. Okay, so let's talk about carbocation rearrangements and hydride shifts. Okay, so when you have this carbocation, I have been talking about how these orbitals overlap and pull electron density, right? Remember when I was talking about that before? So when you have this carbocation in here, it has an empty p orbital and a positive charge. Now, this right here was that sp3 orbital, wasn't it? Okay? They're right next to each other. So when you have this positive charge and have these electrons there, they're going to be being pulled over this entire time, right? Okay. And so these things are going to rearrange quite often, actually. And what you're going to see is that this hydrogen is going to actually have its electrons pulled over, and it's going to move with them. Okay? Now, the hydride shifts are the most common of these. I'm going to talk about another version of these that can happen, but the hydride shifts are going to be the most common, okay? One of the ways you can help your brain accept these things is that when you're looking at bonds, they're constantly stretching and deforming all the time, okay? Kind of like somebody sitting there playing with their keys, right? Everybody's seen that before? Or sitting there playing with a fidget spinner? Okay. Every now and then, what happens to the thing they're playing with? It goes back to its normal, but what else happens every now and then? Every now and then, they drop it. Yeah. And so bonds do the same thing. They're always deforming. And yeah, normally it just goes back to its normal state, right? The lowest energy state, that's the normal thing. But every now and then, they're going to dissociate. And then they usually snap back together because they're more energetically efficient that way. Okay? But what happens if you have something else that can pull it over? It's going to get pulled over, right? So the other way of thinking about this is actually constantly snapping off as a hydride. And if there's something to react right there next to it, it can do it. Okay? Anyways, that's a hydride shift. The electrons in the hydrogen move over. This specific one would be called a 1-2 shift. And that's because we're migrating the hydride to the adjacent one. Okay? You can have other hydride shifts that can occur. Like if you can wrap back around and have a carbocation that can come back around and start playing with the other hydrogens, you can actually draw those over. Okay? But that's the hydride shift. Now I had mentioned something else. What if you don't have any hydrogens to do this with? Well, the carbon bond also has electrons in it, right? Carbon-carbon bonds. Yeah, the carbon weighs a heck of a lot more, so it's going to be a lot harder to do, a lot slower. But yeah, you can actually pull those carbon bonds over, and that's going to be a carbanion shift or alkyl shift, depending on who's saying it. Typically, alkyl shift is the better way to do it. And so what's going to happen is this carbocation is going to pull the electrons for this alkyl group here, and it's going to shift that over. Mm-hmm.
So is this kind of like they're fighting over the...
They are.
Okay.
Yeah. It's literally you're desperate for food. You're sitting next to somebody that has food, and you reach over and take their fry. I mean, I'm not joking. It's literally, this is a positive charge. It has a orbital that's going to look like this, right? This one has an orbital look like this. The electrons are popping around all the time, right? And so if the electrons get too close over here, they get pulled over. Yeah. And that's the essence of that. It's going to happen randomly. It will typically settle down on the one that's the most stable. And so you'll have it spend more time as the one that's more stable. If there's a big enough stability difference, you'll see a big enough, almost all of it will be on that species. Okay. Now the thing to keep in mind here is if there is a hydride shift available, the alkyl shift is never going to happen. Okay. And it's again that same idea of you move the chair, not the table, right? Because the proton is a fraction the mass of an alkyl group, right? It's much, much lower mass. Okay? And so protons are going to move far faster than a alkyl group can shift. Okay. By the way, it doesn't actually matter which alkyl group shifts. In this case right here, it could have been any of those three. It doesn't matter. Okay? So the lighter one will shift faster. So if there's a longer chain, that's not going to usually shift. But yeah, it can shift any of those methyls. It doesn't matter that's up, down, left, right, whatever. Okay. Okay, so let's talk about the driving force of chemical reactions. So for a reaction, it reflects the extent to which the reaction favors products over reactants. This is the same thing as we had been talking about thermodynamics. Does anybody remember thermodynamics versus kinetics back in general chemistry? What the difference is? Okay.
Kinetics is like how fast it'll happen, and thermodynamics is if it's favorable, like if it'll happen at all.
Exactly. Which direction will you spontaneously go in? And so will it happen on its own without you driving it? That's thermodynamics. Kinetics is how fast you can get there, right? And another way of thinking that is the energy barrier, how large the energy barrier is. Yeah. Okay. And two very different things, right? Yeah. Like, why don't you go to the bottom of the ocean right now? Thermodynamically, very favorable, right? Kinetically, very, very slow. Why haven't you oxidized yet? Thermodynamically, you're going to oxidize, aren't you? Yeah. Kinetically, it's going to take a bit. Yeah. So your driving force increases with increasing stability of your products relative to reactants. That's that thermodynamic difference, right? The more stable your products are, the lower energy they are. If they're much more stable than reactants, then thermodynamically, you're going to eventually get there, right? May take more in your lifetime, but you're going to get there eventually. Reactions driving force is generally going to increase with greater charge stabilization of products relative to reactants, greater total bond energy in the products relative to your reactants. That was that Hess's law stuff that you did way back in Gen Chem, okay? Where you took like the delta H's, added them together throughout a reaction, and figured out if it was negative or positive, right? Or you took the delta S's, or you took the delta G's. Okay? That's what all of those were. So this right here is going to be the charge stability. The charge stability actually is usually more important than the bond energies. But the charge stability and bond energy can both differ across a reaction. So for example, right here, we have the charge stability happening right here, right? We have nitrogen positive versus nitrogen neutral, okay? And then we also then have a HCl bond versus an NH bond, right? And so we have both things happening. This proton transfer greatly favors which side? Yeah, products, right? Way bigger than 1, right? 10 to the 43 very much favors products. So your charge stability favors your products here. In this case, we have a negative nitrogen, less stable than a negative chloride, right? And that's due to the electronegativity and the diffusion of that charge, okay? The other thing we then have is the bond energy actually favors reactants in this case. The HCl bond is actually a more energetically favorable than the NH bond would have been. So we're seeing here the charge stability greatly outpacing the bond energy differences, right? Yeah. Which is kind of interesting. You didn't think you'd see that today, did you? Yeah, good stuff. All right. Now, charge stability usually wins these differences. It's pretty unusual for it not to win. Okay, it can not win. That is possible, right? But you have to have some very specific conditions. Usually, overall charge stability usually wins this. The bond enthalpies or bond energies are usually not as large. And so again, this one, the charge stability is going to favor your products. The bond energy is actually going to favor reactants. And so the side that's favored is likely the products. Okay, so this right here is an allyl cation. What are we noticing about that allyl cation? what are those different, like, states that it could be in? What's that called again? They're not enantiomers this time. These are actually resonance structures. Okay? Or Kekulé structures is what you call the individual ones. Okay? So this is one structure that represents what this really looks like. Okay? The Lewis structures in and of themselves, and the ones you can actually write out according to the rules we play this at, don't actually fully encompass what the real structure looks like. Yeah. So in reality, what's happening here is this allele cation, it actually shares the electron density between as 1.5 bonds between these carbons. Okay? It has positively charged carbons on both ends. So these two carbons are both positively charged. Okay? Thank you very much. This right here is an oxocarbenium ion. Notice again, it has resonance structures, right? It can share that charge density between the carbon and the oxygen. If you're trying to pick up the desk and carry it by yourself versus picking it up with two people supporting each end, which is more stable? Two people, of course, right? If you can share that charge density, that's going to be more stable. Okay? And so additional resonance structures are going to help you stabilize charge densities. Okay? And this makes a very, very large difference in charge densities. This is why, remember carboxylic acid? Okay? Alcohol, not usually called an acid, right? Carboxylic acid, usually called an acid. Okay? Why is that? Charge stabilization, right? With the different resonance structures stabilizing the charge. Okay? Same reasoning. This is the benzyl cation, by the way. This is why we could do that reaction before, is because we can actually stabilize that charge among this benzene ring. Otherwise, the bond energy differences would have been massive, right? Okay, so let's look at the carbocation stability. What carbocations are going to be more stable versus which ones will be less stable. Okay? The carbocation stability, a methyl is going to be the least stable. It has nothing else to share that charge with, right? On the other hand, a primary carbocation has another carbon that it can draw some electron density away from. Okay? And it'll help stabilize that. Secondary means two carbons attached to the carbocation. That's going to help with drawing even more electron density. Okay? And this is tertiary. That means we have three carbons attached to the one we're interested in. Okay? And that's going to further stabilize that. So again, everybody see that trend to stability here? Okay. And remember, carbons with hydrogens around them are slightly negative, aren't they? Okay? So these are actually adding negatively charged groups around here. Okay, so that's the order of stability here. Let's talk about some more relative stabilities. Here we have our methyl, primary, secondary. The allyl is going to be approximately the same as a secondary carbocation. The tertiary then, the oxycarbenium is going to be approximately as stable as that one. Okay? And the benzyl one, which is off the benzene, is going to be about the same stability as those. Everybody understands what this double wavy line means? The equals but not quite equal? It means approximately the same, right? Okay. So, which side of the carbocation rearrangement will actually be favored? And don't answer out loud. I'm going to quiz you. Got an answer in your head? Okay, ready? Set. Go. Okay. And it's the reactant side. And that's actually because, let me see if I have this further here. Okay, which one was more stable, secondary or tertiary? Tertiary is more stable, wasn't it? This one right here is a tertiary carbocation. It has 3 different groups connected to it. This one right here is a secondary carbocation, isn't it? Okay. Okay, so let's look at the carbocations and their stability. So when we have a carbocation, we have one orbital that's now free. It doesn't have anything to put in it, and so it no longer hybridizes. Okay? And so that's actually going to be an sp2 hybridization for the other stuff, and it's going to have one p orbital free, nothing in it, which is the carbocation p orbital. Okay? Empty p orbital, carbon's positive. Right? Now, this is empty space that has positive charge associated with it, isn't it? So every bond that can overlap with this that's near it is going to do what? It's going to have electron density pulled over from it, isn't it? Okay. And so this sp3 hybridized orbital here is going to have electron density pulled over from it into that empty p orbital for the carbocation. And again, that's why it does those hydride shifts, but it also helps to stabilize it, doesn't it? Okay? So you can think of it as a pseudo-resonance structure, right? It's pulling that electron density and sharing that positive charge a bit. Just a bit. So let's talk about the keto-enol tolerization. This is actually an example of bond energies being the major driving force here. And so this is actually the keto form. And see how that's a ketone right there? Okay. This right here is called enol, and that's a double bond next to an alcohol. Everybody okay with that so far? Okay. Okay, now, what you'll notice about this keto-enol form is that this ketone right here, that carbon right there, that's quite positive, isn't it? Because that oxygen is going to be pulling a lot of the electron density from it. Okay? And what it's going to end up doing is it's actually going to be pulling electron density away from this other carbon. Okay? And that's going to make that proton right there relatively positive. And so what happens is that we get a rearrangement where our proton here can be left, and then we can have a proton be brought back on when we move the electron density down into a double bond right here. That proton can then be brought back in. Does that make sense? Okay. Let me show you the mechanism in just a bit. But the important part is this has to happen in the presence of either a base or an acid. Okay? Because you actually have to have a base or acid start this stuff off. It is a catalyst. It won't be consumed, but it's important to get it started. Okay? This is going to form a constant equilibrium in solution where it keeps going back and forth all the time. Okay? So if you have one that's in a keto or an enol form, you're going to end up with both when it comes down to it. This right here is called an alpha carbon. Anybody know why that's called the alpha carbon? Alpha, beta, gamma, that's the alphabet in Greek, right? We have a functional group here. The first one off of that functional group is the alpha carbon. Okay? The second one from that functional group would be the beta carbon. Third one would be the gamma. Okay? Okay, so let's go ahead and look at the mechanism real quick. So right here's the mechanism. This one's going to be the base-mediated one. And so the first thing that's going to happen is the base is actually going to take that alpha carbon hydrogen, that acidic hydrogen. Okay? That's going to leave the negative charge on that carbon. Now, that carbon is negatively charged, isn't it? But what did we see when we had a double bond next to a charged thing? Double bonds are delocalized electrons, right? They can move around. So what's going to happen is it's going to actually make this resonance structure, which is called the enolate anion. Okay? Everybody recognize the naming for these things? 8, kind of like you did for the carboxylic acid, carboxylate. Yeah, negative charge for it being the base of the acid, right? And it's an anion, of course, because it's negatively charged. And it's an enol in one of these forms. Okay. So right here, we're going to have the electrons on the carbanion move into a double bond right there. And then that's going to cause the double bond here, the carbon and oxygen, to move up onto that oxygen. Now, this is going to give you the second part of your resonance structure, which is the actual enolate, by the way. That's the one that's the enolate. Okay? The basic form of an enol. Okay. Now, once you're in that form, what can happen with that proton you had just donated? Well, you got a strong base again, don't you? And so it's going to take that proton on. That will give you the alcohol form, the protonated conjugate base. And that's going to give you the enol. Everybody okay with that so far? Now, if you had an acid, it's just going to do the opposite. It's going to end up with the carbanion. Carbocation, excuse me. We just did the carbanion. So what's going to happen is the electrons up on this oxygen carbonyl are going to come down here to the acid's proton, and that's going to leave behind the electrons on the acid, generating your water. Notice this is now the protonated conjugate acid, isn't it? Okay. It has a positive charge on that oxygen. Everybody see that okay? And it's going to take the electrons in the double bond up onto that, so it's neutral. This is going to leave you with the carbocation right here. Okay. This carbocation is going to pull the electron density from this hydrogen, and that's going to make that very positive, right? It's going to make it acidic. So your conjugate base here is then going to give electrons to that acidic proton, taking that acidic proton. Okay? And again, it's just a double acid-base reaction. See that? Okay. And that's actually going to end up generating our enol right there. Okay. Anybody have any questions about those so far? Okay, now that's actually keto-enol tautomerization, that entire process. It can have several different mechanisms for it, depending on acid or base, keto-enol tautomerization, but it doesn't really matter. It also doesn't matter which side you start on. Can everybody see that? This entire mechanism for both sides is equilibriums, aren't they? So it doesn't matter which side we start. Yeah. It's always going to go back and forth and get the most stable end products. Anybody have any questions about that so far? Okay. These are the relative percentages of keto-enol forms. Some of them are extremely uneven. Overall, the enol forms tend to be less stable than the keto forms. And so you get more keto, less enol. Okay? It's pretty rare for the enol to be more stable. Overall, enols are not that stable and are fairly reactive. So this right here is the enol form. This is the keto form. And we can see that there's not a huge difference in energies, but it's significant, right? And that's why you do see some of the other. Okay? Okay. Why is this important? Why the heck does this matter? Well, if you have, let's say a sugar, okay? Which form are you typically going to see this in? Straight chain, or are you going to see it in a ring form? Ring form, yeah. By far and away, it's more common to be in the ring form. And so in glycolysis, the metabolic pathway that breaks down their carbohydrates, for their energy, this actually has to do this ring opening. And that's a keto-enol isomerization right there that we're going to go through. So right here we actually see the next step after this ring opening so that we can get the sugar in a form that we can do the reaction, the glycolysis. And my God, I need to do more water. Man, my mouth always gets really dry in this room because it's so damn hot all the time, right? Okay. So anyways, So right here, you're going to see the next step is tautomerization right there. Everybody see it okay? Okay. And you'll notice right here is where we're going to get into the, what form is that? That's your enol, isn't it? See that? Okay. Very, very common trick the body plays. It's going to use some form of mechanism, typically very special conditions, or very special conditions due to an enzyme. It's going to take something that's more stable, put it to a higher energy state, and then that's going to drive the next reaction. Okay? So this is actually a pretty interesting trick that the body plays, and with something we're learning from and we've started using a lot more as well. Okay? So anyways, you're actually going to have the isomerase enzymes that will be responsible for helping along this tautomerization of the sugars in the cells. Again, it does not affect the overall energy distribution. It just makes it go faster. Okay? So it makes it so you can replenish that enol form much faster. And therefore, you can do the next step of the reaction faster, which then would draw this into the next form. Okay? Because it's going to push the equilibrium to the right by taking away the product. Okay. Is that making sense? Everybody good? Okay. Okay. Funny enough, that tautomerization reaction, all the reaction steps I just did for you, these are going to be incredibly important once you go into things like biochemistry, med school stuff, if you're doing med school stuff, all that sort of thing. So this was my probably one of the most important chapter groups for that. Yeah. In case you're wondering. Anybody have any questions? No? Okay, well, we're actually done with all the materials that we need to cover before the exam. So we are on track. Okay. Anybody have any questions about the exam for the last minute? I mean, can you? Yes. Totally dependent on you, right?
Yeah.
Okay.